Assalamualaikum warahmatullahi wabarakatuh. Okay, now we look at the electronic spectra of a coordination complex. So the electronic spectra usually will be determined, okay, using UV visible spectrum. Okay, so that is electronic spectra. Okay, so when we talk about electronic spectra, actually we have four types of spectra. Okay, the first one is the ligand spectra, and then the ion pair spectra, and then charge transfer spectra, then the D2D spectra. Okay, for the ligand spectra and ion spectra, okay, so basically you have learned the theory, okay, in your organic class and as well as in your spectroscopy class, because this spectroscopy, okay, because these spectra, okay, are referred to the organic compound. Okay, while for the coordination complex, okay, we will focus on these two spectra. Okay, so it means that from your UV visible you can have a few peak ataupun a few spectrum lah. Okay, so this is your UV vis. Okay, so for the charge transfer spectra, this spectra will divided into two categories. The first one we term it as MLCT, which is the metal to ligand charge transfer. Okay, CT is the charge transfer, and another one, okay, is the LMCT, which is the ligand to metal charge transfer. So we will look into that in these topics lah. And then the final spectra is the D2D spectra. Okay, D2D is the one yang you tengok tu lah, yang the delta O. Kan, yang sebelum ni the previous lecture regarding the delta O. Okay, the difference between the T2G and EG, or the EG and T2G. So that is D2D spectra. Okay. Now we look at the first charge transfer spectra, okay, which is the metal to ligand charge transfer, or we term it as MLCT. Okay, so the characterizations of metal ligand charge transfer is the metal. Okay, this metal has the metal behavior, or the metal selections must be or must have low oxidation state. Okay, when you say it is a low oxidation state, so it means that this metal must have rich in electron density. Okay, okay, to make it clearer, okay, for example, you have CO, for example, 2 plus and CO3 plus. Okay, so CO cobalt berapa? Cobalt is D7, 27 Okay, so they're 27. So it means that the cobalt have blah 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 3D7 4S2. For 2 plus cobalt, the electronic configuration will be 3D7, while for the 3 plus cobalt, the electronic configuration will be 3D D6. Okay, D. Okay, so here when you say about low oscillation state, which is the 2 plus, okay, so 2 plus will be D7. So when you compare the 2 plus and the 3 plus, which is a D6, so the low oscillation state will have higher in electron density, or high electrons lah, because they have 7 electrons instead of 6 electrons for cobalt 3 plus. So that's why when we say about if the metal have low oscillation state, so it means that it must has high electron density. Okay, so that is the metal part. For the ligand pula, okay, so for the ligand untuk MLCT, for the ligand, so the ligand must have vacant orbital, or you can say it has unoccupied orbital lah, to fill up the electrons. Okay, untuk nak fill electrons. Okay, so dia complement with this metal. Okay, so the example of the ligands, okay, that have a vacant orbital, okay, is the Cn negative, carbonyl, pyridine, bipyridine, and etc. So when you look at this, okay, compound, okay, you can straight away imagine lah, okay, or you boleh terus terdetik lah. Okay, so this compound is actually a strong field ligand. Okay, so with a strong field ligand, so sebab itulah dia ada vacant orbital, and sebab ada strong field ligand, okay, so this, okay, based on what you have learned last week, so this will undergo pi acceptor, MOT, molecular orbital theory. Okay, so we move on to the next slide. Okay, so as I mentioned before, the MLCT, okay, will have, okay, ataupun the chosen of the ligand for MLCT is the strong field ligand. Strong field ligand. So with strong field ligand, so based on the MOT diagram ataupun molecular orbital theory, it will group in pi acceptor ligand. So this is the MOT of the pi acceptor ligand. So remember, okay. So for the which peak, okay, which peak will correspond to the MLCT is actually this, okay, and D electrons, okay, and this unoccupied ataupun vacant ligand, okay, and this is the electron rich from metal part. Okay, and this distance between the T2G and the EG, okay, the distance between T2G, sorry, not EG, the T2G and the pi from the ligands will be the MLCT charge transfer spectra. So this is the spectrum. So this value will indicate the spectrums at the UV visible. Okay, ingat so this one, while for the D to D will be here lah. Okay, so daripada sini the T to G towards the vacant pi orbital, because remember the criteria for MLCT is the vacant ligand, okay, vacant ligand orbital, and electron rich metal. Okay. While for LMCT, or the term is ligand to metal charge transfer. So this is LMCT, ligand to the metal charge transfer. So the characterizations for the metal, kita tukar color lain sikit. Okay, so the characterization for the metal is the metal has high in oxidation state. So when the metal has high in oxidation states, so it means that this metal will have empty orbital. Okay, for example, macam tadilah cobalt. Cobalt 2 plus and cobalt 3 plus. Cobalt 2 plus will be the 7. Cobalt 3 plus will be the 6. Okay, so initially the cobalt 2 plus will have 1, 2, 3, 1, 2, 3, 4, 5. Okay, and then while this one will have 2, 3, 4, 5. Okay, so for the cobalt 2 plus, so this is the electron 1, 2, 3, 4, 5, 6, 7. For the cobalt 6 plus, 1, 2, 3, 4, 5, 6. Okay, so dia ada empty orbitals lah. Yang ini maybe tak nampak sangat. So kalau you buat splitting, then you can see the empty orbitals. Okay, so that's why it when we say if it has high in oxidation state, so it means that they will have empty orbital at the d side lah, ataupun d orbital. Okay, so that is for the metal side. What about for the ligand? So for the ligand part, so the ligand will rich in electron. Okay, ataupun kita boleh cakap the ligand has high electron density. Maksudnya dia kaya dengan electrons. So what are the ligands that is rich in electrons? So those will be your fluoride, bromide, and etc. lah. And then again, when you look at this this compound, okay, straight away you know this compound, it is a weak field ligand. Okay, so with the weak field ligand, sama juga what you have learned regarding the MOT, okay, will be the pi donor MOT. Okay, so kita tengok the MOT diagram. If you look at the LMCT MOT diagram here, okay, so you can straight away know this MOT belongs to pi receptor ke donor, pi donor ligand. So the charge transfer spectra for LMCT is between this energy level towards the metal energy level. Okay, so you have two metals here, metal side here, so the EG and the T2 G. So sometimes, okay, the LMCT you can have two peaks. Sebab apa? Sebab dia ada vacant orbitals at T2G and ada juga vacant metal orbitals at EG. Okay, sebab remember again for LMCT, the criteria for the LMCT, the metal has vacant orbital, ataupun kita boleh panggil dia ada empty orbital. Okay, so if the metal has empty orbital at T2G, so it must have empty orbital also at EG. So that's why you will see two peaks for LMCT usually lah. But sometimes you can also observe one peak, okay, that correspond to this EG, the ligand towards the EG pun boleh. So sometimes you can observe two peaks for the LMCT, and sometimes you can also observe one peak at LMCT. Okay, sebab apa? Remember, this is the metal will has vacant orbital while your ligand has rich in electron. Kan kaya tu. So basically, now, okay, you can think of, okay, the electronic spectra is actually the electron movement, okay, from one energy to the other energy level. Okay, so when we talk about movement, okay, the movement of electron, so bila kita cakap movement means pergerakan, so it must have two types of, okay, so the first one is the forbidden movement, ataupun we term it as forbidden je lah, forbidden. Okay, so the next one is the allowed. Okay, so macam mana kita nak tahu, okay, that particular complexes or compounds is forbidden or is an allowed transition. Maksudnya forbidden movement or allowed movement. Macam mana kita nak tahu? So based on two selection rules. So we have two rules. Okay, two rules. Okay, untuk bagi tahu whether it is a forbidden or allowed. Okay, so the first rules, okay, is the Laporte. Okay, so the Laporte selection rule. Okay, so the next one is the spin selection rule. Okay, so kita tengok satu-satu. So now we look at the Laporte number one. So how do you say that movement is allowed or is a forbidden transition, or is it an allowed transition? So in Laporte rule, so kita tengok dia punya azimuth number. So what is the azimuth number? So flip back your inorganic lecture. So this we term it as L. Ingat lagi tak? The L. Okay, so basically you have L equal to 1. Okay, L equal to 2. Or L equals to 0. Ada. Okay. So this is what the Laporte selection rules will refer to. Okay, so for an allowed transition, okay, for an allowed transition for the Laporte rule, okay, so the delta L must be positive or negative 1 value. So it means that, okay, the transitions between S to P, okay, to D will be an allowed transition. Okay, faham? And then the allowed transition also, okay. Sebab apa? Sebab bila you tolak dia punya azimuth number, you will get 1. Okay, so the next one is the G dengan U. Okay, so bila dia ada change in G and U, so it will consider as allowed transition. So apa ni G, apa ni U? So G will be the yang you belajar T2G. Ingat tak lagi tak? U is T1U. Dia apa lagi? Yang bawah tu will be the A1G. Okay, so that this one will be G. Yeah. So between this energy level, okay, so it will consider as an allowed transition ataupun the S level, S to P, P to D, where your delta L will be positive 1. While for the forbidden, okay, nak guna warna apa pula? Alah. Okay, for the forbidden transition, so bila dah kat sini, the azimuth number equals to 1. So for forbidden transition, the AL must be 0. Okay, and then you have the G or the U. Okay, so with these transitions, maksudnya dekat level yang sama lah. So it will be forbidden transitions. Kita akan tengok contoh-contohnya nantilah. Okay, and another one. Okay, so this one will be based, okay, these rules based on octahedral geometry. So what about tetrahedral? So for a tetrahedral, okay, so bila you buat tetrahedral, so you have 4 bonds. So this 4 bond is actually mixing, okay, with the P and D orbital. Dia bukan P orbital sahaja ataupun D orbital sahaja. So dia mix P and D orbital. So this tetrahedral geometry usually, okay, they group as partly allowed because there are the criteria allowed transitions and as well as forbidden transitions. So they group as partly allowed. Next, we look at the second selection rule, which is the spin selection rule. Okay, so when we talk about spin, so it must you must determine lah the S value ataupun the MS. Can remember? This one you have learned in your inorganic class dulu tu, the MS value. So for an allowed transition for the selection spin selection rule, okay, ambil ni allowed merah lah. For an allowed transition, so the delta S must be 0. So for example, you have MS yang for 1 ni ada 1. So the next level, the MS2 ni ada 1. So the difference between this will be 0. So it means it has an allowed transitions. Okay, while for the forbidden transition, untuk selection rule so for the forbidden transition, of course your delta S, okay, is not equals to 0. So it means that it has value. So for example, okay, you have D2 metal complex. Okay, contoh So example, you have D2 metal complex. So this D2 metal complex has an octahedral geometry. So it means that it must be arranged like this. 1, 2, 3, D2G. Okay, D2G at the bottom and EG at the top. So when you say about D2, so it means that it has 2 electrons. Okay, and then at another level, this D2, okay, can excite. Kan, satu dia excite. So they will excite here ataupun dia excite yang ini. Ikut pandai lah which one, either one. Okay, so it will excite satu. Okay, so kita nak tengok whether bila dia excite, so it means that it has absorbance. Betul. So you will see the peaks in your UV vis spectrum. So kita nak tengok whether this peak yang ada dekat UV vis spectrum is an allowed ataupun is a forbidden peak. Okay, so macam mana kita nak tahu? So kita tengoklah selection rules, spin selection rules. Okay, so one of the selection rules lah, yang tadi tu lepot to one thing, and then yang ni kita tengok the spin selection rules. So for here, the S, okay, the S will equals to MS ni equals to what? So ingat MS ada dua je value, which is positive half and negative half. So here dia ada dua je spin or dua je electron, so it must be positive half plus positive half. Betul? So it is 1 ataupun 2/2 lah, 1 lah. What about here? So the MS, okay, so yang ini pun positive half plus positive half, which is also 1 ataupun 2/2. Remember, this is not negative half. Sebab apa? Positive half is spin up, negative half is spin down. Means walaupun dia naik tapi dia both spin up, so it must be the MS, total MS value must be 1 lah, separuh tambah separuh. So bila kita tengok di delta S, so this delta S equals to 0. So it means that this absorptions is an allowed transition. Okay. Okay, now we look at another example. Okay, so the next example will be D5 metal. So this D5 has octahedral geometry. Okay, so kita tengok spin selection. Okay, spin selection untuk D5 octahedral. So whether the D5 has allowed transition or forbidden transition for spin selection. Rules lah, spin selection rules ni. Okay, so D5. So you have D2G, then you have the EG here, then you have again sama lah T2G, and then you have EG here because it is an octahedral geometry and it is D5. So kalau you arrange D5, for example, this is a D5 high spin complex. So you arrange 1, 2, 3, 4, 5. Okay, and then dia boleh excite. So kalau katakan this electron excite, okay, so dia naik atas. So what happens? So this will happen. Okay, sebab yang ni dah penuh dah. Okay, so dia tak boleh dah naik atas. Jadi macam ni. Okay, so dia turun. Okay, so what is the S value? Sebab ingat kita nak tengok regarding the spin selection rules. So kita tengok the spin ataupun the S value. So the S value for here, yang the first one ni will be half plus half plus half. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, or equals to 5/2 ataupun 2 half. Okay, so this is the S value. While this one, okay, yang the second compound ni bila dah berlaku absorption, so it means that dia ada satu peak at the UVBs, for example. So what about the S value here? So half, and this one half plus half plus half plus half. Okay, so half times 4 plus 1 spin down negative half. Okay, so it means that the S value for the second compound will be 3/2. Okay, so kalau kita tengok kat sini, ni when you calculate the delta S is not equals to 0. Sebab yang ini 5/2, this one 3/2. So memang value dia tak sama dengan 0. So that's why this D5 high spin, okay, for this peak ni, okay, so the spin selection rules will be forbidden. Okay. So what about another example for a tetrahedral complex pula? Kan, okay, kita padam ya. Pause sekejap. Okay, we look at D to D transition juga. Okay, but for tetrahedral complex. Kita tengok juga the spin selection rules. Okay, so for kita pick one compound, okay, for example COCl4, okay, 2 minus. So it means that the CO ni will have 2 plus oxidation state. So CO2 plus, kalau you buat electronic configuration blah blah blah, you will get the 7. Okay, so kita arrange sebab dia D to D transition. So kita arrange lah, because this is a tetrahedral. So the T to G will be at the top, the EG will be at the bottom. Okay, so bila the side, so sama juga, the T to G at the top, the EG will be at the bottom. Okay, so this is a D7. So 1, 2, 3, 4, 5, 6, 7. Okay, so bila ada excite 1 electrons, so for example here dia naik atas, okay, so dia jadi 1, 2, 3, 4, 5, 6, 7. Okay, nampak? Alright, so kita tengok, because this is a spin selection, so kita tengok the S value for the one here. So 1, 2, 3, 3, 4, 5. So 5 times positive half plus 2 times negative half. Okay, sebab ada dua arrow ataupun 2 spin yang point down. So you will get 3/2. What about here? So the second diagrams ni. So S will be 1, 2, 3, 4, 5 juga. So 5 times positive half plus 2 times negative half. Then you get 3/2. And then you tengok di delta S. So this delta S will be 0. So it means that in a tetrahedral geometry, your delta S is 0. So it means that they are the spin allowed transition. Okay, sebab apa? Spin selection dia allowed. So what about Laporte? Okay, so again, Laporte for tetrahedral is partly allowed. Okay, sebab it is a tetrahedral complex. Okay, now we look for another example. Okay, now we look at another example, which is a charge transfer. So whether this charge transfer spectra is Laporte, allowed or forbidden, and spin allowed or forbidden. Okay, so kita tengoklah contoh dia. So as we know, the charge transfer is actually you transfer electrons, okay, from one orbital to another. Kan? For example, from one orbital to another ni, to other, for example, from ligand to metal, ataupun vice versa, from metals to ligand. Sebab charge transfer is the metal ligand charge transfer ataupun ligand metal charge transfer. Okay. So when you have one compound, so your compound is your MnO4 negative. So mula-mula macam biasalah, you have to know the atomic number of Mn. So Mn, you have 25 atomic number. So you have to find the oxidation state of the Mn, okay, where you know your oxide is -2 charge. So you have 4 oxygens. So times -2, okay, plus your M, your metal. Then this will equal to -1. So your metals will be +7. Okay, so it means that your Mn is 7 plus. Okay, so bila you write your electronic configurations of Mn sahaja, so it will be blah 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 3d5 4s2. So for Mn7 it will be 3d0. Okay, but kan, walaupun dia D0, it means that kalau you buat di splitting, okay, the T2G dengan AG splitting ni, okay, it still have color. Kan, walaupun tak ada electrons pun yang jump, okay, dekat D orbital, but it still has color. Okay, so the MnO4 minus ni, the color is very dark lah, dia dark purple macam tu. So how does the color observe? Okay, walaupun you don't have the D to D transitions. Okay, so the color is actually comes from the charge transfer, not the D to D transition. Maksudnya color of this manganese complex, okay, datang dari charge transfer, okay, bukan D to D. Okay, so again berbalik kepada soalan kita, okay, whether this charge transfer has Laporte allowed or forbidden and spin allowed or forbidden. So kalau kita tengok sini, terang-terang Laporte has the electrons tu dia ada dia transfer to one orbital to another orbital. So it means that kalau P to D, for example, so they have value of the delta L. So the delta L will be equals to 1. So when the delta L equals to 1, so it means that it is Laporte allowed transitions. Okay, so kita tengok pula spin. So again, Mn ni you tak payah tengok pun dia punya d orbital. Why? Because the d orbital is 0. So it means that the movement of electrons is actually based on the ligand and metal orbital. So kita kena tengoklah ligand dia apa. So ligand dia is oxygen. So oxygen ni have 2 charge minus. So initially oxygen is 8. Okay, bila you buat electronic configuration 1s2, 2s2, 2p4 with O2. So the electronic configuration will be 1s2, 2s2, 2p6. Kan, 4 tambah 2. Okay, regarding the negative 2. So dia dapat ni. So when you build your energy level tu, so you will have 1, 2, 3. Okay, so yang ini 2p6 from the O2. Okay, so you will have 1, 2, 3, 4, 5, 6. So you have your 3D here. So your 3D is 0. And then when one electrons excite, okay, and then you will observe the absorbance. So excite toward the higher energy. Okay, so you will get, this is your 2p6, and then this is your d orbital. Okay, so this is your d orbital, 3d. Okay, so this one, bila you excite, so dia akan jadi 1, 2, 3, 4, 5. Satu excite, yang bawah ni excite, so dia akan jadi bawah juga. Okay, ingat yang bawah ni, yang point downwards excite, so dia jadi bawah lah, because here is an empty orbital. So, okay, berbalik, as I mentioned before, it has Laporte allowed. Okay, so you tengok the L value here, the L value for P, L value is equal to 1, L value for D equals to 2. Dan ini L equals to 2, L equals to 1. Okay, bila you cari the delta L, so it's actually 1. Okay, so bila 1, so it has Laporte allowed transition. What about the spin? So spin here, yang ni dah dia jadi cancel out, because 1 over half tolak 1 over half, so dia jadi 0 lah. So this cancel out, cancel out, cancel out, so S will be 0. While here, this one cancel out, this one cancel out, so yang ini jadi 1 over 2. This one negative 1 over 2, so still cancel out, so S will be 0. So this delta S will be 0. So dia bukan saja Laporte allowed, for this complex it also has spin allowed transition. Based on the previous slide, okay, when you observe your UV spectra, okay, kalau you nampak macam ni, okay, for example here, so you nampak a shoulder here, so this, okay, will correspond to the John Taylor effect. Okay, you tengok, you flip back your notes lah. So this John Taylor effect ataupun also termed as tetragonal distortion, so sama je. Okay, so you boleh lah Google up, okay, the John Taylor effect of the tetragonal distortion. So this is actually, okay, what happens, okay, when you say the John Taylor effect is where you have other possibility of degeneracies. Degenerate. So when your complex has other possibility to degenerate, then you can observe the John-Taylor effect. For example, you have D1 metal complex, okay, and it is an octahedral geometry because the John-Taylor effect observed on the octahedral geometry. Okay, so with D1, so you have 1, 2, 1, 2, 3. Okay, so you have T2G and EG. So your one electron can occupy here, or this one electron can occupy here, or this one electron can occupy here. So it means that with D1 you have 3 possible orbitals, okay, ataupun degenerate lah untuk you nak fill up your electrons, and this possible orbital is at the same energy level. So with this criteria, you can observe the John-Taylor effect. Okay, other than that, kita tengok pula D2. What happens when you have a D2 complex? Okay, do you have the other possibility of degenerate? Okay, you have T2G, EG, so you can either have that arrangement, okay, or you can have this arrangement, or you can have this arrangement. So you have a few arrangements juga. So you ada 3 possible ways to fill up the electrons. Okay, so then you can observe the John-Taylor effect. Okay, now we look at the D3 bar. Okay, so you have T2G, and then you have the EG. So the T2G, okay, you arrange your electron like this. Satu arrangement je, you tak boleh nak ubah dah. Okay, so with this, your electron ni won't ataupun non-degenerate. So when you have a non-degenerate orbital, okay, so you won't see your John-Taylor effect. Okay, kita ambil contoh satu lagi pula. A D4. Okay, D4. So okay, 1, 2, 3, T2G and EG. So D4, for example, this is a high spin D4. We have 1, 2, 3, 4. Okay, so it's either you fill up this way, okay, or you can fill up this way. So you ada 2 possible ways to fill up the electrons. So that's why with D4 high spin, you can observe the John-Taylor effect. What about the low spin? Okay, kalau low spin. So if a low spin D4, 1, 2, 3, 4. So you can arrange this, or you can arrange like this, or you can arrange, like this. So you have 3 possible ways juga. Okay, so you ada a few ways lah. Okay, so 3 possible ways. So D4 with high spin and low spin complex, you can observe the Jahn-Teller effect. Okay, so what is Jahn-Teller effect actually? Effect yang macam mana you boleh nampak with your octahedral complex ni yang tekankan sangat. Okay, why this Jahn-Teller effect is so important? So let's look at the next slide lah. Now we look at the Jahn-Teller effect. Okay, so why this Jahn-Teller effect is one of the important criteria, okay, to look into coordination complexes. So why is that? Okay, so we just jump into an example lah. Senang je nak tengok. Okay, so for example, you have D3. Okay, so D3, when you write up your electronic configurations, you will get T2G3 and EG0. Okay, if you draw, okay, your energy level ni, okay, so this is the T2G and this is the EG. So this is how you fill up your spin or your electrons. Okay. And as I mentioned before, the Jahn-Teller effect, okay, the Jahn-Teller effect only for the octahedral structure. Okay, tak ada structure lain for the octahedral structure. So that's why you arrange like this. Okay. So here, okay, remember each of the degeneracies will have its own orbital. So this one, it has dxy, dxz, and dyz. Yang atas ni x square, y square, and z square. So, okay, kalau kita lukis pula, okay, the structure for this example. Okay, so this is how it looks like because it is an octahedral. Okay, and then this is the electrons. Okay, this is the electrons yang fill in dalam the orbital. So if you look at these electrons ni yang fill up dalam the orbital ni, okay, so the electrons ni, okay, is in between the axis, the x, y, and z axis. Okay, so it means that they fit here lah, dalam tengah-tengah ni. Okay. So for an octahedral geometry, sebenarnya dia tak duduk in between the axis. Okay, so the ligands ni sit on the axis. Okay, tapi bila D3, okay, you fit the electrons ni fit in between of the axis. So all the ligands ni, all the ligands, okay, so all the ligands will experience equal repulsion. Kenapa equal repulsion? Sebab dia ada electrons in between ni. Setiap ni ada. So setiap ni ada repulsion yang sama. Okay, so you will get a regular octahedral structure lah. Okay, maksudnya you get a regular octahedral structure, maksudnya distance panjang bond ni will be the same, the angles also the same. Sebab apa? Sebab the repulsions ni sekata. Sebab semua ni ada elektron, so semua akan repulse sekata. So you will get a regular octahedral structure. And but what about if you have, okay, D4 complex. Okay, D4 ni kita ambil D4 for high spin complex. So your electronic configuration will be T2G 3EG 1. Ataupun kalau kita lukis kat sini T2G EG 1, 2, 3, 4. Okay, so kat sini macam biasa dia akan guna XY, XZ and YZ. Over here dia akan guna Z square. Okay, so if you look at here the ligand, okay, this ligand ni, okay, dia ada elektron, okay, dekat Z axis, kan, dia ada elektron dekat Z axis. So this is Z square. So dia ada elektron dekat Z axis. So it means that based on this octahedral structure, okay, the Z axis will have more repulsion. Okay, sebab ada the electrons untuk metals ni dia duduk dekat Z axis. Okay, so dia ada more repulsion berbanding dengan X and Y axis. Okay, more repulsion for Z. Okay, dari X and Y axis lah. Okay, so bila you ada high in repulsion, so you will eventually have high in bond length. So it means that your Z axis will have a longer length rather than the X and Y axis. Okay, contohnya dia akan jadi macam ni lah. Okay, so this phenomena we term it as John Taylor elongation. Okay, sebab dia elongate at Z axis. Okay, so for the compression, because the John Taylor dia ada elongation and compression. For the compression, dia vice versa lah from this structure, and vice versa from the explanation.